fluorine attached to a hydrogen, right? Your dipole is going to have partial charges. So you have an electronegative atom, right? And it's going to have a partial positive, partial negative next to another molecule that has partial positive and partial negative. And that's going to be dipole interactions. London forces, everything has London forces, right? So when you guys have the questions on there, most likely it's going to ask you the strongest intermolecular interaction. Okay. Not going to say which ones you have or whatever. If it says give all of them, right, do the strongest and then work your ways down. So pay attention to the wording on the question. I'm going to go really fast because this is all review. For recrystallization, it only works with solid organic compounds, and it works well when you have a small amount of impurities. That doesn't mean you can't do it if you have like 50 and 50, right? So 50 of your desired, 50 of your impure stuff. It just means that it's just a more difficult techniques. And you guys already know that when you guys did it in lab, it was really difficult for you guys for that 10% already, right? Because one, that's the first time you did it. Another time, recrystallization is just very finicky. Like even in industry, it's a very finicky process. Okay. So don't worry if you didn't get 100% of what you should have gotten, right? It's a learning process. All right. So when you look at these compounds, it could have been transtylbene, oanesic acid, or salicylic acid. Those were the three potential that you have, right? So in theory, when you go ahead and get your optical solvent, right, you have three different criteria. One, does not dissolve readily at room temperature. Why, guys? Why do we not want it to dissolve readily at room temperature?
Because then it's too solvent and you won't be able to get it back out when you're trying to cool it later.
Exactly, right? We're using temperature differences in order to separate things out from each other. So we're doing a physical change of heating and cooling. So if it dissolves at room temperature, there's no way of getting it back unless you just evaporate all your solvent and you're back to square one. You still have your impurities in there. Okay. So we need it to be not dissolved at room temperature, but soluble, fully soluble in the presence of heat. And you need to have it fully soluble in heat because you need all your molecules to actually be a uniform solution, right? Everything needs to be in solution at that point. Because if you have any solids there, it allows for crystallization no matter what. Okay. So it needs to all be in solution. And then afterwards, you need to have it, right, once it's cooled down to actually form that first solid called nucleation. And it should be your desired compound. And then it becomes that crystalline lattice structure where it's only pulling selective molecules of your compound. So your compound becomes that solid, right? It's more pure. And then your liquid, which is the solvent, is going to have the impurities present. Solid and liquid, we can physically separate it out using that vacuum filtration. So, three criteria of how an optimal solvent should technically work in lab, right? And why you're doing that. The next thing is going to be looking at the structure of this. I have my hands right here. It does that automatically. What solvent would technically work? So you need to know the names of the solvents. Okay. So with transtylbene, that being nonpolar, name a solvent that would technically work for this theoretically.
Mm, like pentane?
Pentane would work, right? Because pentane is nonpolar as well. So you guys would talk about the nonpolar characteristics of both. Therefore, it should technically work, right? Theoretically, right? What about oanesic acid? Name a solvent that would theoretically work for that. Let me give you a hint. No, there's no wrong answer for oanesic acid. What would you say?
Anything but pentane.
Anything but diethyl ether. Diethyl ether works as well. Diethyl ether is a polar solvent, right? So with that, you would say that's a polar solvent. Therefore, it should interact with that carboxylic acid or right that ether group on that oanesic acid. Oh, that's great. Awesome. So if you were to say something like toluene, right? Toluene is right here, right? I would not mark it wrong personally, because if you say this has a aromatic ring and this one has an aromatic ring, they have somewhat similar polarities. You don't want it to be too polar, right? so that it dissolves at room temperature. So that might be actually a good contender as well, right? So you have to just be specific of why you're explaining things. Okay. So functional group names, talking about relative polarities. Does that make sense? So theoretically, both of them should technically work. However, right, you just need to make sure that you explain it in context of the theory. Salicylic acid as well, that would be a polar solvent. Okay. So with that, these are the solvents that we used in here. It got the wording got moved when I copied and pasted these slides. So don't worry about that. The first one is going to be your pentane and then your toluene and then ethyl acetate. This is your isopropyl alcohol and this is water. Okay. So you should know the structures of these and know what you're talking about when you're doing some kind of question like that. Okay. Here's the same thing, right? For just a depiction of what's happening, that crystalline lattice structure is going to go ahead and form. You can physically separate it out using vacuum filtration. Vacuum filtration uses that little filter paper. Filter paper is very porous because it's made out of paper, right? It allows for the water to go ahead and go through. Solid stays on top. Physical separation. Pure, pure, right? On top. Your impurities in the bottom. Next is going to be molecular representation. So if you look at your Lewis structure, partially condensed, condensed, and molecular formula, is one better than the other? Yes, depending on the situation. So why is Lewis structures more better than your molecular formula? Anybody, just guess.
Mm.
It gives more information.
It does. It gives you connectivity, right? And it tells you about electron pairs, et cetera, et cetera. Whereas the molecular formula just tells you
Oh
there's
boy.
3 carbons, there's 8 hydrogens, there's 1 oxygen. Good luck trying to figure out where everything goes, right? Lewis structure will actually tell you the connectivity and will give you more information. However, it does get a little busy. Therefore, partially condensed structure is probably what we use a lot in organic chemistry because you can see that functional group of that hydroxyl group or alcohol group right away, right? So there are, pros and cons for each, and you should be able to go back and forth in each. If they give you a Lewis structure, you should be able to do a partially condensed, right? If they give you partially condensed, you should be able to go and draw the whole Lewis structure in theory, right? At this point. All right. So when we look at the functional groups, you guys need to know the names. You guys need to know how to spell these things, and you need to know how, the relative polarities and intermolecular interactions that they have. That's what we've been working for towards the whole semester so far. Okay. So remember, alkane, alkene, alkyne, just one letter difference is 3 different types of structures. So spelling counts. Okay. With the alkane, alkene, alkyne, benzene ring, those are all nonpolar. Therefore, the strongest intermolecular interaction is going to be your dispersion, right? Or London or van der Waals. If you only have that functional group present. Remember, the squiggly lines means that there's other stuff, but if we just focus on those functional groups. All right, so which ones are going to be able to hydrogen bond? What functional groups are able to hydrogen bond?
The ones with
Ability.
oxygen.
The one with oxygen, not all of them with oxygen, but they should have an oxygen,
Basically,
right?
just the bottom row, right?
That has that can hydrogen bond. So remember, hydrogen bonding happens when there's an oxygen, nitrogen, or a fluorine directly attached to a hydrogen.
Oh, I guess
So
and
which one can
alcohol.
hydrogen bond? Looking at these ones,
Carboxylic acid,
carboxylic acid,
Alcohol.
alcohol,
amide.
amide, and amine if it's a nitrogen with a hydrogen on those. Okay. So those have the potential to hydrogen bond. Right. And then everything else, right, with the oxygens has the dipole, right, as the strongest if depending on what it's actually binding to. Okay. Remember, like for instance, right, TLC, we have the groups of the OH. So silica has the OH groups on there, therefore it has the ability to hydrogen bond. So although like menthone, if you have 2 menthone next to each other, they're not going to hydrogen bond, right? But menthone attached to silica will actually have the ability to hydrogen bond because we have that OH on here. Do you guys see that? Awesome. Okay. So it just depends on what it's going to bind to, or if it's just like, a solution of just itself. Okay. All right. Looking at that, TLC works. So when you have your short essays or whatever, I would suggest you guys to have the techniques that we use, and then in a paragraph write down how it works to do separation, or how it uses for characterization. Okay, that's my hint. That's extra work for you guys, but it will help you guys out. Okay, for that.
Can you repeat that one more time? Sorry.
Yeah, so I'm saying with all the techniques that we have, I would say write out a paragraph of how that technique works and how to purify or characterize. Okay, so that's just the theory part of it. Basically, like an introduction of all the techniques that we use. All right, so for TLC, we have menthone, limonene, p-toluic acid, and diphenylamine. When we go ahead and do TLC, which one is going to have the highest RF? In theory, we're going to go ahead and null what we had in lab, okay? In
Limonene.
theory, which one is going to be the highest RF? What did you say?
Limonene.
Limonene.
Limonene, awesome. Limonene is going to be nonpolar, right? Therefore, the strongest interaction is going to be not dipole, dispersion, right? So since it has dispersion, van der Waals, right? That's going to be the weakest. Therefore, it's going to be able to move up the highest. So the highest RF. What's the next one?
Menthone.
Menthone, right? So menthone's going to be the next one with the highest RF, right? Because it's going to be able to only hydrogen bond once, right? Diphenylamine is going to be able to hydrogen bond twice. And your p-toluic acid has the potential to hydrogen bond 3 times, right, to the silica. So therefore, right, this is going to be the highest RF, and then menthone, and then diphenylamine, and then p-toluic acid. In theory, right, looking at the ability to hydrogen bond with the molecules. So a hint is draw all the partial charges, partial positive, partial negative, and then looking at partial positives and negative here, where can things interact? Okay.
Can you explain really quick why diphenylamine bonds twice and why p-toluic acid bonds 3 times? Because I know they can. Like,
Yes.
I have it memorized that they can, but I don't understand why.
Yeah. So right here you have that partial charge. So this is going to be, yeah, it's a very complex thing. So it's actually a really good question. Don't worry about that. So that nitrogen is going to have that partial negative, right? That
Mhm.
hydrogen is going to have that partial positive. So looking at here, right, you have that partial negative,
Mhm.
partial positive. You have 2
Oh, okay.
that you can bind to, right? So this negative, right, can interact with this positive.
Okay.
This positive can interact with this negative.
Okay.
Very good question. Okay, so you have 2 potentials of hydrogen bonding.
Okay.
All right. Next, alkane nomenclature. Remember, with the nomenclature, I am going to give you a table.
That makes so
if
much
there is
sense.
a question like this, okay? Because this is not a lecture class. So I want to make sure that you guys can actually fully understand it. So when you guys have this, you guys can do well on those first 10 questions. Okay, that's my hopes and dreams. And then you can have it set for you guys for your final exam for your lecture material. Okay. So that you can do well in your lecture. And that's the point of them making me do all this stuff. They're mean to me, but it's to help you guys. All right, the IUPAC system. It has to be in order. You have to memorize this, okay? Parental chain first, name of the substituents, location of the substituents, and then assemble the name. Okay, so it has to be in that one. Remember the example that we did in class, right? Try to do it on your own, okay? It has the answers on there, so just keep on trying out stuff. All right. For the next one is column chromatography. So we have fluorine and 9-fluorinone, right? With these 2 different compounds, we're separating it out using column chromatography. So it's technically about the same kind of theory of TLC. However, we have different mobilities. We're moving down a column now, right? So with this, our compounds are going to separate due to the differences of the interactions. Fluorine is going to go ahead and have your what dispersion forces. So that's going to be the strongest because that is a nonpolar compound. Your 9-fluoronone has that ketone group that can interact with your alumina. Alumina is going to be a dipole-dipole interaction. Okay. So since the interactions are going to different, your compounds are going to go ahead and move off of the column at different rates. So it's basically like this, right? The one that is going to be weaker affinity, right, meaning the more nonpolar compound, is going to come off the column first. Your compound of your 9-fluoronone, which is going to be the polar compound, that one is going to still be able to move down the column, but it moves slower, right? Therefore, that slower movement should be making it separate from your fluorine. So fluorine and 9-fluoronone technically should be moving at different rates, right? And you should be able to get separation. But I already know a lot of you guys got 9-fluoronone, right, out at the beginning fractions. Just means that the binding probably wasn't as good, or something happened where you were just having things move too fast. In order to separate our compounds, we're physically doing collections with those fractions. Okay, so fractions are able to be used so that we can physically separate it out, because that's what the point is, right? We're trying to separate one compound from another compound, so we're using different fractions. The more fractions at smaller volumes usually indicates that you're going to get pure fluorine and pure fluoronone. So if you collect really big fractions, you're not going to probably get good separation. Okay, so it's always better to do more fractions at smaller volumes. All right, so for your cycloalkanes, when you look at a lot of those cycloalkanes, you can go ahead and see that, especially like cyclopentane, right? The little triangle one, that one is going to have a lot of ring strain. Okay. However, your cyclohexane is going to be very nice and it wants to have that chair conformation because it has no ring strain. Okay. A lot of rings, right? They're really rigid. You don't want rigid molecules. Rigid molecules means that they're unstable. However, cyclohexane is going to be a very stable molecule when it's in the chair conformation. And the reason for that is because that angle strain is going to be virtually the same as your hybridized carbon in an sp3 hybridized carbon, right? So your carbon-carbon carbon bond angle is going to be 109.5 degrees, which is exactly the same as the sp3 hybridized carbon 109.5 degrees. So since there's no angle strain, it makes it so that it wants to do that chair conformation. Another thing is that torsional strain. There's no torsional strain because the R groups on the carbons are going to be staggered with one another, which is going to be very ideal. It's going to be staggered. Therefore, when it is staggered, right, it means that there's no like steric hindrance. Okay. And that's going to make sense over here. When we have the axial and the equatorial substituents, all of them usually alternate, right? They alternate up and down. So if you only have 3 groups up opposed to all 6 of them up at the same time, it makes it for more room for these substituents, right? More space. So that's what they're talking about the torsional strain. All of the R groups are going to be staggered from one another. So they're going to be either, they're going to go up, down, up, down, up, down, right? Alternating. So there's not going to be that much strain on that. Does that make sense? Same thing with the equatorial, right? The equatorial, it's going to go up and down. Therefore, there's no real steric hindrance for these. That's why it's actually very nice that cyclohexane is going to have that chair conformation because there's no angle strain or torsional strain. Right? With your cyclohexane, there's going to be a ring flip. So you need to make sure that you guys can go ahead and draw these parallel lines and how these parallel lines are drawn. And then you're going to be able to ring flip them. With the ring flip, your values, right? If you start on 1 on that corner, it all goes clockwise 1 over. So it goes clockwise 1 over, and it just goes numbering. So your 1, right, goes down there, your 2 goes there, 3 goes there, 4 goes there, right? And your parallel lines go ahead and change. There's no way for me to explain it but just practice those ring flips. Okay. And that's all you need to know for that for this class. All right, so stereoisomers and diastereomers, okay? Enantiomers, mirror images, non-superimposable. Diastereomers, non-mirror images, non-superimposable as well, okay? So when that, you're going to be able to look at structures and determine if things are enantiomers or diastereomers. Memorize this, okay? Enantiomers, all stereocenters change. Diastereomers, some stereocenters change. And this is the example that we went through, and a lot of you guys had light bulb moments, which I always enjoy, right? Each one of these are going to be enantiomers of each other because all of the stereocenters change, right? All the wedges turn to dash, all the dashes turns to wedges, okay? Whereas when you go ahead and look at all these examples, right, these are all diastereomers of each other, right? And they're all diastereomers because only some change. So there's 3 stereocenters here. So 1 or 2 stereocenters change between those molecules, right? So enantiomers all, diastereomers some. Okay. Make sure you guys remember that. All right. So next is going to be talking about the resolution of enantiomers, and because this is more complex, right? So the resolution is going to be just a fancy word to say you're separating a racemic mixture. You're purifying and trying to isolate one enantiomer from another enantiomer. Okay. In order to do so, we have to go ahead and treat it with something. We have to do an acid-base reaction to form that diastereomic salt. Okay. The reason for that is because enantiomers are going to have the same kinds of bonds. Okay. And with the same kind of bonds and the same just mirror images from each other, it means that these physical properties are going to be the same. So IR is the same, melting point's the same, boiling point's the same, right? Solubility is the same. Everything is the same. So if you have everything the same, there's no way to actually physically separate things out, right? We have to have some kind of differences in order to separate compounds. And that's why we're going to go ahead and treat it with an acid base, right? In order to form that diastereomic salt. Specifically for our experiment, we used that proline, right? That proline was added, it reacted, theoretically, right? Theoretically reacted with our racemic mixture, forming the SS salt and the RS salt, okay? The SS salt was less soluble, right? The SS salt was less soluble, therefore it precipitated out. The RS salt should have stayed in solution, okay? So we use solubility differences of these forming these 2 salts in order to separate them out. With that, now we have that physical separation. We go ahead and get our final, right? We treat it still, et cetera, but we get our final solid. And with our final solid, we go ahead and get a percent yield. Our percent yield, theoretically, our maximum, right? And our desired should be 50% because we start off with a racemic mixture, right? We start off with a racemic mixture, we should get 50% in theory. So when you calculate your percent yield and you analyze your number, you should be analyzing it to 50%, right? So if you have something like 40%, usually for other reactions, if you have 40%, you guys usually say it's decent because it's like a little bit less than half of what you should be getting, right? 40%. However, in the context of this experiment, if you're getting 40% out of 50%, that's really good. You're only losing 10% of what you should be desiring. Does that make sense, guys? Awesome. Another thing is that if you get 65%, that's not good, right? If you get over 50%, that's not good because you know at least 50% is going to be your undesired enantiomer. Okay. So you want something that's under 50%. Cool. All right. Pay attention because this is for your post lab anyways. All right. So the next thing is going to be your optical rotation. That's going to be found by your polarimeter, right? So you have your angle of rotation. Your angle of rotation should be a positive number, right? So this is a positive whatever number. Your concentration is going to be the grams of your product divided by that 10 mils of acetone. right? And remember, everybody's concentrations should be technically different because everybody has different amounts of grams that they got overall at the end, right? With that, you could go ahead and put it in these equations. These equations will be given to you guys if there is calculations on the exam, okay? So you don't have to memorize these two, okay? With this, you're going to go ahead and put your angle of rotation, whatever here, positive value in there. L is going to be 1 decimeter because that's our sample cell. Your concentration is going to be whatever you have on there, right? Grams per 10 mils. With that, you should get a positive number, right? So you should get a, geez Louise, a positive number, right? Whatever you get, you should be comparing it to the 173.3 degrees, that positive 173.3. Yes, Justin.
Grams per 10 milliliter because all of our polarimetry tubes only hold a max of 10 milliliters.
Yes, it should be grams of 10 milliliters. And it's
Okay.
not only because that polarimetry cell, it's basically when you put it in that volumetric flask, you put
Mhm.
that solid in there and then
Yeah.
you dilute it down to 10 mils.
Yeah, it's the line. Okay.
Mm-hmm.
Okay. Perfect. Thank you.
You're welcome, right? So with that, you should be comparing that 173, right, 0.3. This is your theoretical. This is literature value, right? So your value, whatever you get, compared to that 173, are you close to that value? Are you far away from that value? Why? You don't have to say why yet, but you should be saying, oh, I'm not there yet. Oh, I have 2/3 of what I'm supposed to get. Oh, I have 1/2 of what I'm supposed to be getting, right? So you should be comparing about your values with that. Then you could go ahead and calculate your optical purity. Your optical purity is going to be taking your value, right? Your positive value, dividing it by that 173.3, right? Times by 100, right? That will give you percent EE, right? Same thing as optical purity. Okay. I just like having it named percent EE because it basically says what it is in the name. For example, if you get 30%, like how that pre-lab question was, if you have 30% EE, that means that you have 30% more of one enantiomer than a mixture that is racemic. Okay, so let's think about that. That 30% is only given because of that angle of rotation, right? So it says that 70% is racemic. And I know it's racemic because think about it, right? If you have equal but opposite, right, values, it's going to be at 0. The value, the angle that you get only gives you an angle if you have more than one enantiomer present. Okay. So if you get an angle, then we could do all the calculations. So we could get that 30% EE. Everything else is racemic, meaning that there's equal amounts of that positive and negative, not contributing to that angle of rotation. Does that make sense, guys? Awesome. Okay. So now,
I'm sorry. Just want to back in. The top of the fraction over on the optical purity of the mixture, what is that value again? What is the...
That's your number that you calculated for your concentration. So it's plugging in your angle of rotation, right? Dividing it by 1 decimeter, dividing it by that concentration. That's your number. Because I'm not putting a number because everybody's going to get different numbers on there.
I'm sorry, the equation next to it. So the...
Oh, yeah. So whatever number you get from here, you put it into here for that
got
equation.
it, on the top.
Yeah. Mm-hmm.
Okay.
Awesome.
And then I just wanted to clarify, so the percent EE, the 30%,
Yes.
that is the calculated major enantiomer, and then we have to add half of the...
That's not major yet. That just means that you have
Okay.
more of one, but it is
Gotcha.
contributing to the major.
Okay.
All right. So with it being racemic, now how do we know how much of each one we have in that racemic mixture? We divide that by 2. That's why we get that 35%. So 35% of each, right? So now to get that total, right? 30 plus 35 equals 65% major, right? And then 35% minor, right? And major just means the one that you have more of that enantiomer. Minor means you have less of that enantiomer, right? So it could be positive or it could be negative depending on what your situation is. In this case, since we're doing the positive enantiomer, right? Makes more sense that that major enantiomer is going to be that positive enantiomer, right? Your minor is going to be
Question,
less.
Professor.
Mhm.
So the 70% was given to us, or
It was just calculated. I just made it up. I just used that same example that we had in the pre-lab quiz.
oh, okay.
Mhm.
Okay.
You're welcome. All right. So when you analyze and conclude everything, you're going to look at your numbers. What is the whole objective of this experiment? We want to go ahead and isolate one enantiomer from another. So you need something that's going to be closer to that 50%. Of that, whatever percent you got, when you analyzed it and got numbers, did you get a lot more of the major than the minor? Okay. So we want 50% and we want 100% of our major, right? So how well did it work? I would say not too well. It's pretty decent, right? Because we started off with 50-50, but now we have 65-35. So we did get a little bit more of our enantiomer that was desired, but it's not close to 100%. Something like 80% to 20% is pretty good, right? And then if you got 95 to 5%, really, really good, right? 100% to 0%, what we really, really want. Does that make sense, guys?
So our minor is not the other half of the racemic mixture then.
Yes, our minor is the other half of the racemic.
Then
Right,
shouldn't
so
we
if you
be
think-
wanting 50-50?
We do not want 50-50 because we're trying to isolate only one enantiomer. We
Oh,
only
that's
want the S
true.
enantiomer.
Okay, I see what you mean. So like this is our very final vial.
Yes.
If we
our
have
final
5%
thought.
left of the impure crap that we don't want and 95% of the good stuff, then we're doing good. Okay.
Yes.
Okay.
Of the crap, yes.
Gotcha.
Sorry. Sometimes you guys use the words and it
Yeah.
I'm sorry. I didn't mean that. I'm very sarcastic too. All right, cool. Does everybody understand this? If not, then come to my office hours. This is your post lab, right? I want you guys to get 100 out of 100. I don't even know how much your post lab is worth. Whatever you get, I want you guys to get the maximum, okay? Because I'm trying to help you guys out. All right, guys. Have a good weekend. Good luck on your studies. All right. Come see me in office
Bye,
hours if you have
thank you.
questions.
Thank you.
Bye, guys.
you.
Good luck. I'm rooting for you guys.
All right,
We also
everybody. I
have a
hope you
quick
enjoyed
question
watching
to
this.
ask you.
Yes. What is your question?
That is the
It's
end of my
regarding
stream.